Right. So I think this is the last lecture uh, today. We will have a full session on something which is very interesting aspect in computational astrophysics. There's people are now basically when you are dealing with astrophysical systems, we all know that the majority component of astrophysical systems is plasma. So what we have been doing up till now is basically solving the plasma properties and understanding the plasma properties using MST equations, treating them as single fluid, treating them with a very simplified inversion state of some equations, and we are solving them with whatever methods that we have learned. In this little lecture that I have, maybe in half an hour or so, what I'm going to introduce is basically an alternative method to actually solve plasma. I mean, to understand the diagnostic property of it. Now, essentially, if you look at, if you look at basically the physics part of it, everything comes from statistical mechanics. When you say when you always study, let's say this symbol or something like this, you can either study its length and its velocity and so on, or you can basically go and look at each of its molecules and try to understand the same process. Apply force on this table. So when either compute this displacement of a table as a whole, and then look at each of the atom how it is displaced by my force. And it's the same thing. The answers will come out to be the same. But it is of course more tedious to look into each atom. It's just impossible to look at each atom. Rather, it's much easier to approximate as a bulk. But in several astrophysical systems, which are dealing with plasma, it is not always appropriate to actually treat them as single fluid or an image or just as a fluid. So there are underlying assumptions in which you can treat them as a fluid and in which you cannot treat them as a fluid. For example, one of the most critical assumptions of fluid approximation is collisionality. So essentially, if I take a fluid element, the basis is that if I take a fluid element, it's to be highly dense so that it's fully collisional. Okay, so if it is fully collisional, that element ka velocity I can define, temperature I can define, density I can define. But what if there is only one particle in that fluid element, that small region? Then you cannot treat them as collisional systems. They become collisionless. Now, in such kind of systems, you cannot treat them as a continuum. So you cannot take like thousands of electrons and बोलेंगे कि ये one entity. You cannot do that. You have to treat those 1,000 electrons as 1,000 separate entities. Okay, and you have to basically solve them separately. So there is a region where the system becomes collisionless. In those kind of systems, we cannot apply our MST equations, which is essentially under an assumption of collisionality. Instead, what you need to do is collisionless systems for kinetic physics. So instead of, like, you can take an example of a gas molecules in a box, right? I mean, you can always basically define a pressure of that kinetic theory. You write Boltzmann equation. Boltzmann equation is the fundamental equation that describes the distribution function of how the molecules are distributed in space. But then from there you can define the pressure, you are defining the temperature. Why? How can you do so? Because you are assuming all these are kind of identical molecules, they're interacting with each other, they're collisional and so on and so on. But if in a box there are just two molecules, if there are just two molecules, will still the system hold true? Will hydrodynamics hold true? Not right. Then you will have to really go into your solving the Boltzmann equation. So that's the approach that we will demonstrate. I will demonstrate I will demonstrate today. Just at least give you a brief introduction of how basically it works. Right? So give you some introduction preliminaries, and I'll discuss about algorithms. I'll give you a little example, but it's just one image. It's just one image of it. But there are very good books which gives a much more detailed description of this process, which is called particle in cell. So it's studying clearly now. So we are now approaching from uh, density, velocity, magnetic fields to something much more fundamental, that is distribution function. Now we will be basically going from, let's say, 3D Cartesian space to 6D phase space. Okay. So now you have to basically orient yourself into phase space or Cartesian space. And there are some very fundamental books which are written in. This is one of the Bibles, Plasma Physics by Computational, Irshad and Langdon, and it's very good. I've also adopted some of the images from here in my talk. Right. So now let me explain you the problem in slightly more detail by giving you an example. Now let us look at solar wind. Solar wind is basically stream of plasma that connects between sun and earth. Now in this figure, on the top, you will find you have landscapes going up from 10 to a minus 2 to 10 to 12. Okay, this is in meters. Okay. Now you can see different things here that I explained, but each bar has a color. Okay. Purple color is near the corona, so near the origin of the solar wind, and the cyan color is near Earth. So what is the value near the Earth and what is the value near the sun? And then there are these different properties. Like for example, these two. So this is the mean free path of a proton. What is the mean free path? It's basically the minimum distance it travels before the collision. So this is the length of the system. Length of the system kitna hai? 1 astronomical. I mean sun and Earth. This is the length of our system. Now you can see the mean free path of the proton is very exactly similar to the length. In fact, the mean free path exceeds the length of the system when you are approaching L1. That means proton wouldn't have even collided once to basically to reach L1. So, how can we treat all protons as a fluid? Okay. Similarly, there are other terms here. So essentially, this rho e and rho p are essentially the gyro radius of the electrons and the protons. Are much smaller. Okay, they are much smaller. But so the idea is that we need to solve the physics here to understand what is happening at larger scale. These are called as Debye lens. So Debye lens and plasma are very fundamental lens, which are essentially providing something like a skin depth. So the plasma in general is basically like a quasi-neutral system where you have electrons and protons. But let's say if you put a test charge in this thing, then what will happen is if it's a positive charge, it will attract all the negative electrons towards itself and form a shield around itself. Okay. So it's electric field. If I put it in free space, how is the electric field of a unit charge? So it's like, oh, with radius कैसे जाएगा? But if I put it in a plasma, you would see that it goes as 1 by r squared e to the power minus. So it will basically exponentially decay हो जाएगा. And so that is something like a screen or a cloud, given which its electric field will decay. That radius of that cloud is called the Debye. So this is the fundamental characteristic lens plasma. Gyro radius also, when you are essentially having electrons and magnetic protons and the magnetic fields, the fundamental gyro radius of this system. Okay. So now if I want to treat each of these protons and electrons in the fluid, because I cannot treat them as a fluid anymore, I will have to worry about the different set of equations that I need to worry about. Okay. So it's very, and of course, time scales are different. I mean, also almost mentioned about how the time scales are different and closer to the mergers and far away. Similarly, in solar wind, there's a huge slew of time scales. Okay. So either you can do MHD, but then you are incorrect because the fundamental assumption is incorrect. Okay, of collisionality. So the equations of MHD only holds in a collisionality aspects. Now we know that the mean free path is such large as comparable to system scale. So how do you do it? You cannot basically treat them as a fluid, but now we have to treat them each one as a particle. So then you have to go for each particle and try to understand. So now if I am going to go for each particle, what is the force that will act on a particle? Lawrence force, Coulomb force, right? Lawrence force basically. So essentially, so we have to basically solve it like a multi-body system where the force is basically acting as the Lorentz force. So now we have to change our mindset from fluid approximation to particle approximation. Right. Right. So coming back to the basics. So let us go one step back and try to see that what were the fundamental equations that were used to derive the emission. So as you can see, we had the hydrodynamic equation and we had the Maxwell's equation. And so Maxwell's equations are much more fundamental. Hydrodynamic is already assuming collisionality. So let's go back to the Maxwell's equation. Because the Maxwell's equations are far more fundamental. Okay, it basically determines a charge structure or a charge entity. You can have a single charge, or a multiple charge, or a cloud of charge, or a current density, and the Maxwell's equation still holds. Okay, so the idea is that in particle and cell, you essentially solve the Maxwell's equation. Forget the fluid equation. You directly solve the Maxwell's equation. When you have an electric field, you have a magnetic field, you have a current density J and a charge density rho. And of course, the averages of V to be zero. But the beauty is that if you look at this equations here, you can combine the first and the third equation to write basically the current continuity equation. So the charge density, rate of change of charge density, plus divergence of this current is basically zero. So essentially, you can eliminate one of the two equations. So if I solve this equation, I don't need to solve these two equations together. I can only solve one. And if I basically prescribe my magnetic field such that divergence of V zero, it will always be zero because you're solving the Maxwell's equation by definition. Okay. So essentially, these two equations cut out, and so you are essentially left with just two equations to solve, and of course this one. Okay. So now the idea is that you have a charge density, current density, and you have the evolution of the magnetic fields and the electric fields. And remember here that the charge density which is coming from here goes here into the source. So they're kind of coupled in some sense. Now, of course, when you want to define charge density, you need to know how the charge is distributed in space, in momentum space, in Cartesian space or in the coordinate space, and in the momentum space. And that can only be governed by your distribution function. Okay, so you know everything about the phase space distribution function. All these things you must have studied. So the idea is that you can write basically the evolution of the distribution function. So essentially, in collisionless systems, you have something called the Lewis theorem. Have you heard about Lewis theorem? What is Lewis theorem? Anyone can? Phase space volume. Phase space volume is conserved in collisionless system. Right, but essentially, if you have collisionality, then you can have on the right hand side some collisionality term. Okay, but the phase space volume is just basically expanded derivative in phase space. So you have essentially a term corresponding to the special derivative and a derivative in the momentum space, and you have a force which is acting on this. And if I have an electron proton, force will be the Lorentz force, Q E plus V close to. Okay. So essentially, you have to solve this equation in combination with this and these two. So now your equations have changed. Now you are no longer in the MHD domain. You are now treating individual particles, or essentially a group of particles. But they are kind of experiencing the electric field and the magnetic field without basically, because of its motion and so on. Because of its current generated, charge generated, and so on. So this is basically a set of equations now which are your concern. Okay. So now how do you solve this equation? You cannot adopt the same approach of Riemann solvers, hyperbolic, parabolic, that doesn't work. So we'll have to adopt some alternative approach, kind of combine these equations and solve it in the computationally possible manner. You can always basically do this. You can just solve this equation because this is like the fundamental of Riemann equations. So you can already solve the Vlasov equation. No problem in 6D space. So you can take 3 velocity and this. So you already know the problem in 2D. Now you have to do in 6D. So think about it, what you will do. Then it will get super expensive computationally. 3D space. So 3D is in the coordinate space and 3D in velocity space. If you want to completely describe the system, so that is essentially how people solve the Vlasov solver. So there are essentially nothing but a partial differential equation. It's just one equation, but in 60. Okay, it's just one equation. Okay, so you can choose to solve this equation. This one is kind of description for class distribution function. Now, if you evolve this distribution function, you can use the moments, for example, the density, velocity, temperature, whatever you want. So you are free to solve this equation in 60, and you get the complete description of the plasma. That's what Vlasov solvers do, and there are Vlasov codes. There are codes in the community, especially space physics community, which do solve the Vlasov equations. So here the idea is that you basically take a 60 space. So here is just in this thing, I'm just showing you in 2D space. It's better for visualization. This is the momentum axis and this is the coordinate axis. And this is the place where plasma is distributed, and here you have a grid. Okay, so you can describe such a plasma by solving this equation and see how this thing evolves in space. So that's what Vlasov does. But you see, when you look at it more carefully, how Vlasov actually solves, so you have much more smoother solution and so on and so forth. Okay, of course, you cannot afford to do full thing, but if you are very smart and careful, you will understand that the properties of this plasma as it translates along the characteristics, like what we did in the hydration equation. In the hydration equation, which was described by Pratik and Dipanjan, we discussed about the characteristics. Everything moves along the characteristics. So if we can actually implement an algorithm, in which we are trying to do this in a Lagrangian frame. Okay. If we do this in some sort of a Lagrangian framework in phase space, so the phase transport, we are doing it in Lagrangian framework, then what we end up is basically sampling these plasma into different particle cells. Okay. So you can think of this plasma now, instead of basically grid, you can think them is basically just these are like squares, or these like plasma like particle bunches. Okay, so these are like particle bunches. So so this is plasma. This is basically described by some distribution function. You can approximate this as one bunch. Similarly, another bunch of particles as one. So you can basically span the whole plasma. Of course, this is much more noisy, but than the Vlasov, but at least it helps you because it kind of completely eliminates the free velocity space. Because you know how the velocity is going to move along the characteristics. So if you track the motion, you are essentially eliminating this velocity space completely. Okay. So now you have these patches, or essentially the bunches of what I call the macro particles in big infrastructure. Then you can track these, how they move, and when they move, they will impose all the properties because these are charged particles. So they will have the currents, they will have so that's the basis behind particle influence. The idea is that instead of doing in 60 space, what you do is you treat the bunches of particles as they move along and adopt it. So it's more in the Lagrangian framework. That is the idea behind such kind of space.
Is there, so are there like some sort of standard sampling mechanisms for protecting these particles? Or?
Yeah, so it depends on the initial condition that you want to provide. So we will look into the algorithm, but the idea, I hope you have got an idea of what is particle in cell. Basically, we are essentially trying to boil down the full 60 space into 3 by basically describing some bunch of particles which will move in this space. And this movement will be decided by the force. Okay. So we are essentially eliminating this part. So we are eliminating a Lagrangian part of this, whereas this part still remains. Right. So now, so the question comes so what is, so if we understand these are particles, the one particle in cell. So why do we need to subtend this particle in a cell which is in coordinate space? We still have to do that. So now here again, you can see there is a very classic description of particle in cell. Here you can see as in 2D, there's a y-axis, there's an x-axis. You have a distribution of plasma. So essentially, plasma is charged particles, nothing else. So this is a distribution of charged particles in some random shape. But let us focus on one particular grid here. Okay. So this has all the coordinates 0, 1, 1, 0, 0, 0. Then there's a charge Q here. Now this charge Q basically is just a particle of charge Q. It is in some, which not necessarily that it will be on the grid center or grid. You need some arbitrary point. But now this charge will contribute to the charge density here, 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 and here. But proportionately. For example, the charge will have much higher influence on this cell than this. So there is like, something called a bilinear interpolation. So essentially, what you can do is, I'll talk about the weighting and all these schemes. There are certain schemes also to weight. So there you can basically decide how much fraction of this charge will contribute to the charge density at this point, and this point, and this point. Okay. So this is basically what particle in cell does. You have a distribution of particles spread around. You can define some random distribution of particles. There's an underlying grid. And because everything works on the grid, we will have to kind of interpolate the contribution of that charged particle on the grid. So how do you do the interpolation? I will discuss about. But the idea is to have some sort of an interpolation. So you have particle in cell. Okay, so cell is essentially the grid structure, and particle is essentially the charge. Okay. So now we have the basic infrastructure in our disposal. Now, even this basic infrastructure, if you understand what the basic infrastructure is, how do I take from my initial condition to the next step? How do I know? How will I basically be able to evolve particle distribution from this shape to the next shape? Okay. So that is a full-fledged, very, very popular algorithm. It is a called a particle instance algorithm. And it's a very interesting kind of four-stage approach. So we can start from anywhere. So I prefer to start from here. It's an easier thing to start from. So let us start from here, and the time basically goes like this. Okay? So we go basically clockwise. So the first step is weighting. That's exactly what I spoke about right now. So for example, you can have a random distribution of particles, provide their fixed positions in the velocities, initial velocities. You can define, let's say, the distribution of particles is following a Maxwell distribution in velocity space. And so you can define, let's say, some temperature, and you will have some sort of a velocity distribution. So you can randomly choose particle velocity from this distribution and some special distribution and basically initialize the particles in the grid space. That's easy. That's give initialization. Then comes the weighting. That's what I was talking about. Yes.
So in each cell, we are getting a fluid approximate average of velocity.
Sorry.
And in each cell,
like so we are initializing particles. So essentially, I have a distribution. I'm drawing random values from this distribution and I'm assigning to the particles. So let's say I assume I have like 100,000 particles. So I have to basically do 100,000 drawing of the distribution, drawing of the random numbers from the distribution. So I will basically have individual particle entities with X and V. Okay. So these are particle entities. Then we can do the weighing. This is essentially the interpolation. From here, it is not necessarily that they will be on the grid center, grid edges, or grid whatever interface. So we will have to do the weighting. And this weighting will give us what is the charge density in this region. So essentially, at the nodes we will basically get the charge density and the current density because we know the charge of individual particles. Let's say you can take an electron or a positron, and you know the velocity, right? So basically, in particles. So for example, if there are a lot of particles near one node, then this will have high charge density, therefore higher current density. If the velocity is high. Okay, it's the current density is NEEV, right? So basically ENV. So that's the That's the current density. So you can basically get the charge density and the current density. Right? So you have the charge density and the current density on the grid. Now let's look at the equation. Okay. So now we have the charge density and the current density in the grid. Now from this charge density and current density, you can compute by solving the Maxwell equation. You can basically compute the EB by solving the Maxwell equation. So essentially, you solve for this E, put this E in there to get B. Charge density E is the B, and you can check. I mean, of course, you can always check for the continuity to ensure that the thing is conserved. Okay, so this is the two equations that you solve. So you start with some initial distribution of particles. You computed its charge density, current density. Using the charge density, current density, you computed the electric and the magnetic fields. Okay. And these fields are computed usually at the phase centers, phase interfaces. Now, if we have the electric and the magnetic field, we can basically then, we already know the particle position. We can compute the electric and magnetic field at the particle position by doing the same way. Okay, because essentially the electric fields will be given here, magnetic field will be given here, electric field will be, because they are vector quantities. Just like constraint transport, no? You have to define it at the edges. You define the electric fields and the magnetic fields at the edges. Now from here, you have to interpolate it back to Q. You have to interpolate it back to Q with the same weighting. Now you have interpolated Q, so the same weighting has to be done to get the electric fields and the magnetic fields on the charge particle Q. Okay. So you can then, with that interpolated electric and magnetic field, you can compute the source, which would be acting on the charge. And then what you do is you use that force to update its velocity and position. So now you have moved the plasma. In the new position now, again you deposit your current and density, this thing. Again the electric field will be updated, allowing the force to be changed, and again this will move. So this is the whole step. Do you understand this? Okay. So the idea is that you started just with random distribution of particles from a distribution, like a Maxwell distribution or some distribution which you thought were appropriate, and then you kind of evolve this system every time step from the first principles, essentially. Because essentially you're treating them as particles, like force experience minus consciousness. Okay. Yes, your question. So the idea is, so that's basically the whole idea behind how this thing. So let's look at the different kind of models or different approaches for each of these stages. Okay. But before we go that, these simulations basically would have fundamental scales. Now, since we are dealing with part plasma, we'll have to do the fundamental scales of the things. So, of course, the velocity is the c. This is the speed of light. Charge is the electron charge. This is fundamental. Mass of electrons. Momentum is given by this. Energy is this. Time is basically chosen. So, essentially, you have something called as a plasma frequency, which inverse of plasma frequency is essentially what is set as the time scale. So all the times in your simulations will be always measured in plasma frequencies inverse. So you have a length scale which is given by c over omega r, because that is velocity over the time. So that is velocity into time. Number density will be given by this, and current density will be given by this, and so on and so forth. So everything will be scaled according to this. All the scales are defined already. So you don't have to change because you are dealing with plasma. Okay. So all your scales are defined. Because essentially the idea is, okay, there is no other velocity you can take. There is a fundamental velocity.
That's not the particle velocity.
So that's not the particle velocity. It's like scale velocity. Particle velocity will be much lesser than that. So, but you have to scale it with some fundamental scale. So that's what particle. So as I mentioned, initialize the position and velocity based on thermal distribution of particles for each species. You can have multiple species. You have electrons, protons, positrons, whatever. Okay. You can have all sorts of things. and then you loop over all particles and project the charge and current density on the grid. Then knowing charge and solve for electric field, and that for any external electric field. You can also incorporate any external electric field or magnetic field if you like in your system. Okay. So that's basically covers the initial part of it. Now let us see into so one of the aspects is basically motion. So it's a very simple problem. I mean, you have to solve how a particle moves from point 1 to point 2 by a force. So this is something very, very simple. So you solve basically the Newton's. I'm showing you Newton here. You can also do in the relativistic case, but essentially I'm just showing you the Newton approach here. So you have dx by dt equal to v and dv by dt equal to f. You essentially have to solve this equation numerically. How would you do it? You must have done this at some stage. Which methods do you use? Euler for Mach, Mach for Mach, RK2, right? They're all wrong. All wrong. All crap. So Euler, RK2, RK4 are all crap. Everything is trash the results. Okay. So these kind of equations, there's fundamental aspect behind these behind these things. That if I basically have some initial kinetic energy, my kinetic energy should always remain conserved in these systems because there is no dissipative. Okay. So if I start with some initial kinetic energy, my kinetic energy has to remain conserved. All the methods that you have kind of mentioned, they don't conserve the kinetic energy. Physically, they are wrong. Numerically, they can do. Physically, they are. Right? So there are methods which kind of conserve kinetic energy and also are done numerically. So, for example, this is one method which is called the leapfrog. So the leapfrog, idea behind this is time and space. So, for example, this, how do you discretize this? This will be x nu minus x old divided by delta t is equal to v. And this will be v nu minus v old divided by delta t equal to f. So, for example, if f is E by mc, this force is a Lorentz force. So what you have to do is first you have to push your v, which you have defined it initially, equal to 0 to minus delta t using this equation. So to push it. So you have to go ultra minus delta t by 2. You have to evolve the system. You have to solve this to minus delta t by 2. Okay, to get the v. So you get the basically the new v old. Okay. And then using f at t equal to 0. So you have x at t equal to 0, e at t equal to 0. You can basically compute f at t equal to 0. And then, but you do ultra backwards. You go in backwards in time. Like v. Now this is your new v old. And now what you need to do is you compute v new. And you have x old, which is essentially x0 and f0. So the idea is now you basically do offsetted in time. So essentially you have v new minus v old divided by delta t equal to f old. And x new minus x old is equal to v new. Okay, or you can do also the average v new plus v new old divided by 2. So first you solve this equation, you get v new. Now that you have v old, you can get v new. And then use this v new over here to compute the x new. And so on and so forth. So this is basically called the leapfrog method, but they are time centered. This will give you a hint here next time. Next time when we see. So for electrostatic field, leapfrog works very good. So there is also the case when we have no magnetic fields. We just take an electric fields. So in such kind of electrostatic case, the leapfrog works well. But if you have an electromagnetic field, which will essentially have the cube leapfrog in term, then there is another method which is called the Boris equation. I will discuss about that. Right. So, so the idea is this. Now, again, it is very important that it is all symmetric in time. And let's keep in mind that it's all symmetric in time. We have oscillating time, so it's all symmetric in time. Okay, so plus delta t minus delta t doesn't matter. It's symmetric in time. Similarly, when you this is a Boris question. This is an interesting again, oscillated by time. In this kind of approach, the idea is that the electric field is updated. So, for example, I have xp of n and up of n minus half. So, just like the velocity, I do that. And then using that velocity, I compute something called as a an intermediate by updating only the electric field at the original time. Right. So you just basically get So that's basically this. UP is here, V minus half. So this is basically push, and this is kind of drift. This is basically a U line is a drift. So you're drifting the UM by some velocity. So it's basically a drift. Then you have a term which is V cross V. So you essentially rotate the whole thing because it's a rotation thing. V cross V is a rotation thing. So you do a rotation to this velocity which is basically over here. And this MVP is essentially nothing but a rotation matrix. And the angle with which it depends will be proportional to the magnetic fields. The way it will rotate, because it essentially the omega frequency with which it rotates is the Larmor frequency, which depends on the magnetic fields. Right? So a particle, when it basically goes on the magnetic fields, it rotates, right? I mean, if you have a constant magnetic field around what will be the magnetic of the particle? Second. What is the radius of that? And what is the omega? What is the omega delta? Omega is d theta by dt. Omega is the angular frequency, the Larmor frequency. That depends on B, right? So the angle depends on B. So that is what you do. And then you basically update the position by again a drift. So you have a drift rotate. So essentially it's a kick. So kick is basically for the x, and now drift rotate. Okay, so that's how you do it. And this kind of method also preserves exceedingly well the kinetic energy. And so does leapfrog, but leapfrog does much better for the only the electric field case. But with magnetic fields, Boris pusher is far better, and it's one of the standard approach using all particle systems. So to demonstrate this is something which you will be also demonstrated in the hands-on session. I've just shown here how the three things. So, for example, it's a very simple problem. I have a magnetic field along this direction. So I put a particle with zero velocity, so it's basically expected is a circle, radius 2. That is basically what I have. So you can see the black line, which is essentially the Boris push, does the best job. The leapfrog kind of behaves nicely, but then kind of behaves because it basically cannot do well for the magnet. Because it's not basically conserving the kinetic energy. So essentially, either it will be spiral in, spiral out, कुछ भी होगा. And the reason for that is because these methods are symmetric in time. And if you have known in classical mechanics, for every symmetry that exists a conservation loop. So for time symmetry, what is the conservation energy? So if you devise your numerical algorithm with time symmetry, then you should ensure conservation of energy. That's why these methods work, and Runge-Kutta does it. Neither does Euler. Because Euler method, if you do delta t minus delta t, it's not the same. So essentially, the symplectic integrators are essentially the class of the integrators which are used in particle in cell simulations to ensure conservation of for these kind of things. So that's the idea behind particle pushers. Yes, right. So the next step or the next part, apart from particle push, is basically to solve the equations for the electric and the magnetic fields. Right. There were two parts here. This is the moving of the particle that we have taken care of, but then there's also integration of the field on the grid. So essentially, we have to solve this equations. This equations here, basically. Okay. So in this case, the best way to do this is an electrostatic pick. That is what also will be shown in the hands-on today. So if you do a 1D electrostatic pick, it's the most simplest of all, which what we'll show. Basically, if you have a 1D electrostatic pick, then you basically do not have magnetic fields. Then essentially your electric field equation boils down to just Poisson equation. And this is your electric potential, and you have del square phi equal to minus rho by epsilon naught. And you already know the rho because from the sound quantity of that. So essentially you have to 0.5, and with phi you can obtain your electric field and everything works. Okay. So essentially you have to solve a Poisson equation. There are several methods to solve Poisson equation. One of the easiest method is do it in the Fourier space. Something what Prayush also mentioned. If you go into Fourier space, it's all going to algebraic equations. If you do your algebra, you get back into your space, real space also. If you are very adventurous, you can essentially write a matrix equation, a finite difference. You write a matrix equation, invert the matrix. If you are very, very adventurous, you can do that and basically solve it. Solve the matrix equation. So essentially, you have to invert a sparse matrix, and you do this. But this is horrible for parallelism. Still horrible. So that's why FFTs are much better. It's easily parallelized. Okay, so this is the idea behind this. So essentially, you can solve this to either the FFT space or essentially by doing the inverting of the matrix. Okay, and then finally, what is important? So what all gels all of this is basically the interpolation. That is the most important aspect. There are ways of interpolating the charge on the grid, and from the grid to the charge, because you have to interpolate from the charged particle, the charge density and the currents on the grid, and the electric field and the magnetic field from the grid onto the charge particle. Two interpolations, two weighting here, on the side. And you have to do exactly the same. You cannot choose one weighting for one thing and another way, then it will be not correct. So whatever weighting, whatever order of accuracy weighting you use for the first case, it has to be used for the second case. Okay. And there are various ways of doing this. So this is basically the simplest of all is essentially the zeroth order weight. The idea is very simple. So if this is the jth cell and if this is the charged particle over here, okay, and this is basically the charge. So this is j minus 1, xj plus 1. So this is the jth cell, and if the charged particle is xi is over here, then this whole charge basically will belong to this. So that's what you do. So essentially, let's take a case basically like this. For another cell here, this basically will become down. For another one, it becomes this. If I keep on adding charge to this cell, not that. It's basically like a flat in the middle. So whatever is this, but if I put something over here, this belongs to this cell. Okay, so essentially you have like if you have extra particle, the charge density will be increasing. So the idea is that in whichever cell you belong to that cell. Basically, no weight. That is the zeroth order weight or the nearest grid neighbor NGN approach. Okay, and the better one is the first order weight, which is actually cloud hill cell. So essentially, what you do is again the same approach with the J cell, but now your charge will have some contribution to the left cell and to the right, because it's kind of lies in between, and it is proportionate. If it is closer to the right, and it will have more contribution to the right cell than to the left. So that's basically called the first order weight of the cloud in cells. Then the check of the current charge density. Basically now in this case will be because essentially they will be linear interpolation. You have this thing, some part will go in this cell, some part will go in this, depending on the distance. That's a linear interpolation. Okay, so you essentially will have a triangular. You can also do spline. You can also do multiple higher order methods. Up to you, but of course they are all expensive. Go on. So you have a cloudy cell approach or the TSC, the triangular shaped cell. So then these are essentially the different approximations or different interpolation things which one does to get this. But it's very critical that exactly same weighting scheme has to be used for both particles and force fields. Okay. So you cannot use for particles NGN and then for force you use first. That's not correct. So that's the idea. And now, what I'm just going to show you are some results. So I think most of it will be shown in the hands-on. So I just want to, because you have done the reconnection problem, I just want to show you how the reconnection, which is far better to be done with particle in cell MHD, because the MHD requires this artificial resistivity. But as we saw in the last class, that everything works with electron diffusion. So it's much better, much more correct to solve magnetic reconnection in particle itself. So these are some results of magnetic reconnection. So essentially here you can see the density. So the density of the plasmoids are kind of separated. So here you can see very clearly effects of these small plasmoids and these big plasmoids, merging of these plasmoids. So this is electron. And you can basically also see here the magnetic fields and the other density. So this is basically the proton density. So that is what it is. And again, you can see that the length scale is C by omega p. So proton in scale of this thing, all the length scales are in C by omega p, the same scale that we used. So the idea is that these are not densities; these are particles. These are actually the particles. Okay. So you are seeing particles here, and the higher number is higher density. That means there are a lot of particles in that region. You have interpolated it, and you are seeing the n densities. Okay, so you are essentially plotting the density. You're plotting the particle, but essentially you're plotting the density, number density. So you can see how large number of particles are accumulated in these plasmoids. And there are more of these plasmoids forming, which makes the connection problem very interesting multiscale. Okay. So I think we will stop here. I just wanted to give you a glimpse of the particle itself. Of course, there are several open source particle and cell codes available in the community. However, Computer basically has some version of particle and cell, but essentially it's combined with chemistry. Right? So that is another approach and a hybrid approach. We don't go into details of that, but there is a version of chemistry than Pluto, and it would be slightly more advanced. But what we will do in the hands-on, what Pratik will do in the hands-on, is to give you an idea of how it is to be, which we have discussed, how it is actually working. And he will essentially solve the 1D electrostatic peak problem. So we can basically do this. So this will be with Python. So I think, right, I think this will be with Python. So I think he will demonstrate this after his lunch. So use Python. Yeah. So what I try to do one tell that any questions or we can start? Yes.
So I have two questions actually. In Euler method that you have, so I have done project in basis that was looked at the orbital length. So basically, we are solving for PIs in 2D objects. So there in Euler, as you have told, because it's the symmetric time step. At each step, I am calculating x I plus 1 and pi plus 1 from xi and pi. And I'm saying that the energy is dissipating linearly. And because of that, we could not use pi. What is the reason for why numerically this is second?
Because it's not time symmetric.
So after that, we could use the leapfrog for distribution, but instead of that, we use something called a modified Euler. So there, that is like we are again taking the symmetric time step, but at each time step, we are calculating xi plus 1 from xi and vi. But while calculating vi plus 1, we are using that newly found xi plus 1.
Okay, so you basically modified all that. But that will also not work.
There we saw that the energy was conserved.
But for not for a very long time. I don't know how much you have indicated. You see, even Runge I can see, I'll show you in this case, no? I mean, this is with, it is with very low resolution in time step. Okay, so if I increase the time step resolution, so I go to much smaller time steps, then they will start overlapping with each other. So Rungekutta will start overlapping with each other. But if you do it for a very long time, there will always be a spread. I think Pradeep will clearly show these kind of things.
I think there is a formal mathematical proof.
Of course. I mean to say
symplectic or
exactly. So there is a formal mathematical proof, but I mean practically Pradeep will show all of these things. So just wait for lunch. All of this, yes. Yes, go ahead.
So I have a question regarding weighting. When we evolve the fields and we try to map them back to individual charges. So it is possible that a certain value of field can correspond to different arrangements of charges which are not identical within a cell. So are we losing some information in that sense?
So you basically have to ensure at every time that this thing is kind of maintained.
Yeah, but we will only get an idea of yeah, exactly. We will only get an idea of densities within a cell, right? We don't get an idea about where exactly the particles.
No, we do, because we have updated the position of these particles. So we always know the position of particles and the velocity of the particles. See, there are two things here. See, this part information also we have, and this information we also have. So I mean, you don't need to interpret exactly those positions. Yes, yes. Yes, Omer.
But this has like too many similarities with those. So like, what's the main difference?
The main difference between n-body simulations and so n-body simulations, I can tell you, n-body simulations, if you do n-body simulations, it's a point to point, right? I mean, so you take 2 points and compute the gravity force, and 3 points, it's a multi-body. What is the order in which you are solving? You are solving essentially order n square.
No, not for if you do the particle mesh method.
Particle mesh. So if you do SPH, there is a different method.
This is particle mesh.
This is particle mesh. This is not particle. N-body is purely particle. Are you talking about SPH?
No, we're talking about gravitational dynamics of dark matter particles.
Okay, but
Essentially the same.
Yeah, it is taken.
It's called particle mesh.
okay,
That's the
yeah. But n-body is different. N-body takes the individual particles.
No,
There is direct n-body, which is like
Direct n-body. I'm talking about direct n-body.
particle mesh.
Okay.
Not direct.
I see. All terminology then. That's why I didn't include it.
So do we have such case in which the CIC interpolation is not fully fixed?
Well, of course, higher order is always good, no? Higher order is always good.
Yeah, it is always, but like
You would like to go from CIC to second order
that
product.
would be good, but like it's not good enough for any problem. Is there?
That you will be very problem. For example, you are asking a total here interpolation is better than parabolic. I mean, it all works in a sense. Okay, so I mean, it depends on how much information you want to extract. That level you want to extract. But mostly people either use first order or even second. Most commercial big boards, or most big boards.
I'm just curious. So typically, what's the size of the, like if you want to do a production run, what's the how?
These are the super expensive. I mean, these are like very expensive simulation runs. I mean, they say I have only done very on the scratch. I can't tell you big numbers. Like, I think more data will be required. But I mean, this simple electrostatic 1D problems will be done on your. So that's not. If you do these large scale simulations, it will be expensive. It will take about 10,000 of CPU hours for just one round. Very complex. So we'll stop here. I think we head for lunch.
Let's like Bhargav.
Cute.